That's the hard part. Where you just gotta keep Googling best practice, best practice. How do I do that? Best practice.
Well, good evening, everyone. Thank you all for coming. I just want to introduce our speaker tonight. We have Professor J. Emerson visiting us from Yale University in New Haven. He is a professor of statistics there. His research ranges from sports statistics to bioinformatics and environmental statistics. He's the author of a few R packages, a package for Bayesian change point analysis, the big memory and related projects for computing with massive data sets, and also the G-pairs data set, which I believe he's going to speak to us a little bit about tonight. And he's also very active in New York City tech meetups in statistics, programming, and computation. So, here's our speaker.
Very happy to be here tonight. I'm going to try to not go for a full hour. I'd rather have you interrupt me during the talk. I've also been given instructions to try to stay over here because of that little camera there. So if I don't drift over to this side of the room, please forgive me. I'm trying to be on my best behavior here. So I hope that you will feel free to interrupt me during the talk. I'm going to show you a range of different visualizations. Some I did, some I didn't. I'm not claiming that any of them are ideal. There's probably room for improvement on any of them, and if something strikes your fancy as particularly good or particularly objectionable, I'd encourage you to say something about it, because I think that everyone really should have an opinion on graphical displays and visualizations. I don't think that there's necessarily overriding principles that need to be followed blindly. At some point, it's a little bit of an art. But what I'm talking about mostly, I think, is some of the technology that's underneath the hood, possibly to create customized visualizations, and certainly to let you deliver some of your visualizations or maybe other summaries of explorations, mostly on the web. And so I'm going to cover a range of materials, all slightly different in flavor. Some of it will be a little bit more technical under the hood. I might even show you some code. And so I hope that there will be a little of everything for anyone, but please do interrupt me as I go through. It doesn't make any sense for me just to talk straight through. So I'm going to get started by, I guess, just showing the abstract. The big picture is that I'll start by talking about some grid graphics programming, and the particular application is a plot called the generalized pairs plot. I'll give you some examples of that, and I hope that maybe some of you will find that useful if you actually do data analysis day-to-day with R. And I'm actually going to use that as an introduction to two different technologies for delivering graphics, visualizations, or applications in general using R on the web. One is by Simon Urbanic down at AT&T, two packages, RServe and FastRWeb. Those provide CGI scripting using the R language, and it's very flexible and powerful. The other is the package Shiny from RStudio that I think some of you have probably heard of. And they both serve similar purposes, but they're really quite a bit different in nature, and I'll try to point out some of those differences and hopefully convince you that they might be worth looking at a little bit more closely. I can't show you the examples actually up on the Amazon cloud because some port is being blocked on the wireless network. However, I will have full materials available after the talk, after I get home, so I can upload them, because some of them were produced on the train. But others were not produced on the train, but were not uploaded. So I'll have a website copied on the website. They'll be available around 11 or 11:30 tonight. So I'm going to start in, but again, please do stop me if there's anything along the way that you'd like to discuss. So everything will be available. And I'm going to start with something I haven't said anything about yet, but you'll see where I'm going in a second. This is called a mosaic plot. Who's heard of a mosaic plot? Okay, about half. That's probably about right. Imagine that you have a piece of paper, and you're going to cut up the piece of paper into regions. And so I've chosen here to divide up this piece of paper vertically. In the background, we have the Titanic data set, and it's a little bit small. I probably should have increased the font size. I don't know if the guy who coded that provided an option for doing that. But since I coded it, I can't make too much. So this is actually, it was originally in S+, and then they grabbed it and sucked it into R. It's just a mosaic plot in base graphics. But if you imagine anything that you would think about exploring with a contingency table, this is just a one-way contingency table, and it's a graphical display of the counts in the variable class in the Titanic data set. And so the areas are proportional to counts. And you can see that the crew in the third class were really quite sizable, and first and second classes were smaller. And the width of the rectangles here then are proportional to those counts in the categories. Now, if you watch carefully, you can introduce a second variable, and I'm just going to go as far as adding survival. And so now we have exactly the same vertical strips, but conditional on the category, we have survived or didn't survive. And so first class was treated fairly well, maybe no surprise there. Second class, well, better than third class, and the crew in the third class had survival rates that were really fairly similar. But again, the principle is that areas in the tiles are proportional to counts in a contingency table. And so the question is, why am I starting with this, and how does it relate to everything that I promised to talk about? And the reason is that mosaic plots are part of the generalized pairs plot that I'm about to introduce. If you'd like to know more about mosaic plots, there's the original paper that I think was back about 98, and once you have these slides, that'll link directly to it. In package VCD, there's a grid version, and that's actually the version that I'm about to use with the gpairs function. And there's older papers. Michael Friendly had something back in 94, and if you go back even earlier, I think one of the earliest references I found was by Hartigan and Kleiner in 84. So this isn't intended to be a comprehensive list, and if you actually wrote something before 84 about mosaic plots, I apologize, and I'd be happy to update the slides. So this is a fairly recent paper called The Generalized Pairs Plot. And it was really a collaboration because we have two different implementations of the same type of plot. We agreed that the name would be a generalized pairs plot. And I did one implementation with Walton Green, who was actually doing a degree at Yale in geology and geophysics, but sort of fell in love with statistics and almost did a master's in statistics along the way to his PhD. We had a lot of fun with this. We implemented a grid graphics version of the generalized pairs plot. And about the same point in time, Hedley Wickham and some of his colleagues implemented almost exactly the same thing for ggplot2. How many people use ggplot2? Okay. Wonderful language. Some people love the grammar and are very passionate about it. Other people just don't prefer the grammar and like to stick in base graphics. Some people hedge their bets and use some of each. But the point is, you have a choice here. If you're enthusiastic about ggplot2, there's a ggplot2 version, and that's described in the paper. If you prefer to use something that's a little bit more conventional in syntax, we're still using grid graphics, but we provide a syntax that's slightly closer to what you would expect in base graphics. And both of these are described in the same paper. It was really a collaborative effort. So there's links to that reference later on. Here's the generalized pairs plot, and here's why I started with a mosaic plot. Who's familiar with a regular pairs plot or a scatter plot matrix? See, I would actually hope that that's a little bit higher. I think that everyone should know about pairs plots, scatter plot matrices. If you do any type of regression or data analysis at all, I really think that it's an important part of the visual exploration of the information in your data set. It helps you explore each of the pairwise associations in the data set. Unfortunately, it's not quite general enough because most of the data sets that you encounter these days have a mix of categorical and quote-unquote continuous variables. And that's all we really did with the generalized pairs plot. We recognized that you might have something that's a combination of continuous and categorical variables. And if you were looking at the association between something that's categorical, like whether or not a country is landlocked. Switzerland, for example, landlocked. Okay? Whether or not a country is landlocked, maybe there's some sort of association between that and environmental performance. Waving my hands wildly, not telling you anything about the data set. You could explore that using side-by-side box plots, for example. If you have two things that are categorical in nature, like whether or not a country is landlocked, and whether or not a country has high population density as categorical variables, that would be a 2x2 table, and a graphical representation of a 2x2 table is handled with a mosaic plot. Now, there's actually two mosaic plots here, and this is interesting because it's an example where the order actually matters. In a particular problem, sometimes you care about the distribution of one conditional on the other, but in other cases it might be the other way around. In some cases you really don't care about one at all, but this is not a symmetric display. It's really two different displays depending on how you view the conditioning when you're looking at the two categorical variables. Now, when you're dealing with something that's continuous and one categorical variable, we've just used two different graphical representations there, trying to help you compare the distributions. I'm sure everyone recognizes the side-by-side box plots. This thing up there we've termed a barcode plot. Maybe it reminds you a little bit of a barcode that you see on the back of almost anything. And so those are just two alternate displays of these conditional distributions. If you have two continuous variables, you see something more like a traditional scatter plot. What we've done here is reduce the duplication of effort in studying the associations. This particular tile, for example, goes hand in hand with that scatter plot, showing the association between the environmental performance index and environmental health. And so down here, we've just got shading. We've reported the correlation. I would expect that at least a couple of people here object to the use of a star to denote statistical significance, but and maybe a reporting of missing values. So this is a generalized pairs plot. It's really just extending the scatter plot matrix in really a fairly obvious way to account for the fact that you have different variables of different types. So let me pause there for a second. Someone has a question? Oh, it couldn't have been that clear.
So the stronger the color, the greater the
So the colors down
relationship?
here would be for examples where we have pairs of continuous variables, quantitative variables, and the degree of the shading is really reflecting the strength of the correlation. Now, correlation may not be appropriate here at all, but you can still calculate it, and you can use that as a basis for your shading, and I would hope that you'd also take a look at that and ask whether there's something suspicious up there. In this case, there's something suspicious up there.
there is?
Does it look a little bit triangular? So
Maybe.
what's happening here actually is that environmental health and ecosystem vitality are the two components that give you environmental performance. It's not a 50-50 average, it's a slightly weighted average, but there's a real reason you get that triangular structure in the upper left. Yeah. Okay. Yes?
You have the scatter plot for two continuous variables, so can we add the fitted line on the plot?
I think that's a great question. So I think that we have an option for adding something to it, yes. And I can't tell you what the option is. I'm not as young as I used to be. But what's more interesting, though, is that if the answer is actually no, we don't do that, the answer is I'd like to convince you that that's the sort of thing you should be able to do easily, because this is written in grid graphics, and I'm a huge fan of grid graphics. It's work that's done by Paul Morrell. It's included in R. You have it already. You just maybe don't know that you have it. And modifying the code to add an additional feature that we've neglected to add is probably less work than you might think. Good. Other questions? One other little example, and this might seem a little bit odd. There's nothing here categorical. So maybe this isn't really a generalized pairs plot. Maybe this is just a pairs plot, and you're not wrong. So you could actually produce a plot very similar to this using the pairs command in base graphics. But it would take you quite a bit of work. It would really be fairly painful. And if you were to ask exactly the same question, could I add a regression line to this plot? The answer would be a little bit different. I would say that in base graphics, trying to modify the pairs function in the way that you requested would be considerably more work than modifying the grid graphics version. I'm not necessarily completely correct about that, but I feel fairly confident in that.
What is the data set that they...
Yeah, okay, so this particular data set?
Yeah.
Yeah, okay. This is a data set where there's, so it's a bioinformatics example where they're studying genes possibly associated with the regulation of lipids, I believe. And they have all these little wells on these microarrays where there's stuff growing. And you can tell right now I don't do a whole lot of biology. But they take pictures. And the pictures show say, green or yellow fluorescing and show objects that are larger or smaller. And they have some software. And the software basically studies those images and magically produces 130 measurements on the image. And some of them reflect maybe the amount of green or the amount of yellow, the size of things. That's really about all I know. So there's 130 variables to explore. I selected a couple at random. And what you see here is that some of them are highly correlated, and others not so much. So just as part of exploring, it might make sense to look at a random selection of these and just to see what you observe. At least you should be reassured that there's not too many outliers. You might ask what the coloring is. The green is for regular gene wells, and the black would be positive controls. And the hope is that maybe by studying differences between the mass of genes and the positive controls, they might be able to focus their attention on certain genes that could be useful for further exploration. There was a question here?
You just answered it.
When you put together a chart like this and showing that certain progressions are significant, is it adjusting the alpha values for the number of regressions in one chart?
No. No. But I'm glad you noticed that, and I would hope you would. And I really don't like that star. Okay. The key here is that G-pairs is implemented in grid graphics. I'm really enthusiastic about it. And as much as I like regular statistical analyses and standard explorations and the sorts of things that you just do day in and day out because you have to explore your data sets, at some point in time, you're going to have a need to do some sort of visualization that's different. And I'm going to show you a couple of visualizations that are different, and there's no way anyone would write a function to do some of these visualizations I'm about to show you. It just would make no sense at all. It's like maybe like a work of art, although I'm hesitant to use that term about my graphics here because it probably doesn't apply. But it's a one-off thing. You're only ever going to do it once. You're not going to make a package to produce this plot and upload it to CRAN because you think anyone else cares about it. So if you're really doing a one-off visualization and being creative, thinking outside the box, a pun slightly intended there, grid is really what you need to be looking at. And so I'm enthusiastic about it largely because it gives me, I feel like it gives me a lot of power and flexibility to do advanced graphics that would be extremely tedious in base graphics. And so I'll show you a couple of examples here and then use that as a segue to the second part of the talk. So I want to just provide some context here. If you think about base graphics and ggplot2, for instance, I'd call those high-level graphics languages. You want to be able to do a scatter plot, you can do a scatter plot. Side-by-side box plots, that's great. In contrast, grid is, I would say, a low-level graphics language that provides you complete control over the graphics device. But as a result, if you want to produce a graphic to do a certain thing, it might take 5, 10, 20 lines of code instead of one line of code. The flip side, though, is that it gives you complete control over what you're doing and lets you develop something new. And so I just want to give you a quick introduction to grid. And again, this is with full credit to Paul Morell down in New Zealand. So I'm going to try to zip quickly over here. And show you a couple things from this slide deck. So, there you go. So whatever this is, it's, let's see, something from a project called the Environmental Performance Index. Oh, I guess you've already seen part of this. You can tell this is a project I was involved with about 2 years ago, and there was an excuse to do some graphics. But this is not the sort of display that you would want to provide everyone else with. It's very specialized. It has to do with this particular application. We're studying not just environmental performance on a variety of factors, but we're also studying trends in environmental performance. It's slightly blurry. I'm sorry that the resolution isn't better. But the key is that you basically have a layout here that includes things like text, rectangles, colors, some lines. That's about it, right? It's amazing what you can do with that. You just need to decide where they're going to go, and you're trying to tell some story that hopefully is accessible to maybe the general public. Whether this is accessible to the general public is one question. Whether it's accessible to a statistical audience is another. But this is an example that was produced in grid graphics. And I'm showing you this because we'll come back to it later in the talk. What's interesting here is not necessarily just the characteristics of this graphics, but the thing that I'm most interested in is the fact that this is actually rendered using grid graphics inside R, inside a CGI script on a web page. And so that's a little bit of a mouthful, but I want to cover each of those topics and give you a sense of how you could do something like this to render a plot like this on the web using R. Okay? Let's see, you've seen that before. Again, produced by GPairs. And so you already have grid. It comes with R. It's underneath ggplot2. It's underneath lattice. And so I'm just going to give you a quick tour through some of the syntax and some maybe very silly examples, but I think it gives you an idea of some of the abstract reasons why grid can be so powerful. And so it is a low-level graphics package. It's not meant to be this suite of functions for producing standard things using a single command. It's for developing new graphics, really. Paul has a book about that, and I'd encourage you to look at it if you'd like to do more. But here's an example. There's a rectangle, and we say hello world. We'll actually say hello world at least 2 or 3 more times tonight, so get ready for it. This little plot or graphical display, if you even want to call it that, it's produced by this code. You have to load the library grid, obviously. You declare that you're about to start a new plot. That seems very sensible. Grid.rect puts a rectangle around the graphics device. Then you have these things called viewports. And what you ought to think of is a graphics device as being a blank slate, and then you're going to do stuff in regions of that blank slate, and those regions are going to be called viewports. Those viewports can be nested. Those viewports can overlap. The viewports can have different coordinate systems. And that, I think, is where the power of grid really lies. You could have a coordinate system in terms of proportional distance, where the bottom left is 0, 0, and the top right is 1, 1. That's one valid coordinate system that can be very useful. In particular, if you want to do something like put text right in the middle, the center of that text is 0.5, 0.5, with respect to the coordinate system that's in terms of proportions. In other instances, you might have coordinate systems that are in terms of units of your data. And that's a very different coordinate system, but a very natural coordinate system, depending on what you're trying to do. And grid provides these different units for your use quickly and easily in a very, very elegant way. And so that's just saying hello world. At the end, you have to declare that you're done with the viewport. So if you have a push viewport to create it, you have a pop viewport to declare that you're done, and you back out to the next level. And so some of these complex plots really involve managing the viewports. At any given point in time, what is your active area? And you have to keep track of that as you create some of these displays. I'll try to give you an example. So, units, RPC and native are the 2 words for the 2 main units. One is for proportional units. The other is for units of data that you can declare depending on the particular problem. And so I'm not going to go into too much detail here. I'd rather leave us time for some of the later topics. But this slide deck will be available if it's not already. And if you have any questions, you're welcome to email me. Here's a more complicated example. Yes, good.
Is indentation important in this?
Yeah, you use Python, don't you?
Right.
I come from a Perl background. And so if I need a scripting language, I'm more apt to use Perl than Python. I'm a believer in squiggly brackets. So we may just have to agree to disagree. I think indentation is absolutely critical, and it drives me nuts when I see code from my students that's not indented. However, it's not required. So interesting. I feel very strongly about indentation in that I like it, but I don't like to be forced to use it for the purpose of something like a closure where squiggly brackets, I think, should exist. Yeah, okay. Philosophy here. So, a more complex example, I'm not going to go into the details, but you'll find examples of each of these uses of units in this example. And so I think that you can actually take these examples, even though I'm not dwelling on the details, and you can build pretty much anything that I've shown you so far or will show you in a couple of minutes. And so I'm going to show you another plot and maybe make that point. This is a plot of the most important football game that takes place in this country. A couple chuckles, okay. The Yale-Harvard game, the very last game of the season, at one point in time, I'm sure it was the most important football game in the country. Now, maybe not so much. So in any given game, Yale scores some number of points, Harvard scores some number of points. The solid lines with the Y's on top would indicate a Yale victory, where the top of the segment is points scored by Yale, the bottom of the segment would be points scored by Harvard. The dotted lines would indicate a Harvard victory, where the Y is stuck at the bottom, and implicitly points scored by Harvard are on the top. So that's one region of the plot, that's one viewport, and inside that viewport you're just plotting segments, some characters, maybe creating a little legend. Notice that there was a break for World War II. There were actually a couple of ties. That was interesting. But then down here we actually have an entirely different segment of the plot, and yet notice that they share a common axis, year. It starts in 1956 because I only actually could find the history of Ivy League games going back to 1956. So since 1956, we have maybe little back-to-back histograms showing victories by Yale and Harvard in the games leading up to the real game. Okay, but this is a different viewport, and it's easy to create a viewport like this that in this case shares units with this viewport for the purpose of a graphical display. Any questions on that? You notice that it's not updated recently? Yeah, we haven't done very well. Here's a completely different example. This actually goes back to the scatterplot matrix that was about the gene array data and lipids that might be associated with regulation of genes that might be associated with regulation of lipids. You notice on the left-hand two columns, on the right-hand two columns, there's a little bit of a pattern. Those are actually alternating positive and negative controls. The gene wells where there's things we'd like to explore are stuck in the center. You see something like that, maybe something like that, lighting up. Those maybe are genes that would be worth exploring. But this is an example produced in grid. The architecture of this particular array is 16 rows by 24 columns. And so within any given well, I've got a little square of space. And recall that earlier I said there were 130 measurements being produced by the software describing characteristics of an image. So the color choice and the intensity of the color is chosen to reflect those 130 variables arrayed, roughly in a 12 by 12 space with a little bit of leftover. Trying to show you exactly what you have here. Yes?
So obviously it sort of stands out that column 24 is different from the rest.
Yes.
So is there a way you can use this producing images for some sort of variable reduction?
Oh, yeah. I could give an entire talk on this. Yeah.
Or identify some patterns of interest?
There's all sorts of problems with this, honestly. I didn't change the ordering of the variables here. I took them in the order that they were produced by the software package. You'd find that if you went back and studied some of the correlations, you get some measurements in consecutive columns, highly correlated. And you might see some vertical structure here. And that vertical structure is exactly that. Yes, you have 130 measurements. Some of them are highly correlated. And you should do something to get around that. We've done a principal component analysis. It turns out that principal component 1 and 5 actually seem to be most helpful in differentiating between the positive and negative controls. And that's actually mostly unsupervised learning. We then explored some of the genes by hand, and we think we have an idea that that's correct. Principal components 2, 3, and 4 were actually doing something funny involved with, I think, killing the material in the cells. And I'm really pushing the limits of what I know. But if that helps, yes, there's a lot that could be talked about here. That right-hand column, by the way, that's neither a positive control or a negative control. That's a different type of substance that they put there for some reason. I don't remember, but you can see how it's almost completely different. More similar to the other positive controls, but we were told to ignore that. Maybe we shouldn't, but we were told to. Other questions? Okay, so I'm going to zip back and shift gears slightly. good. Here we go. So you're going to see why this is a segue. With a little bit of luck, the internet's active, and will take me here. Oh, okay. So you've seen this before. The resolution is much better now. This is actually up on the web. This entire plot is produced by an R script. So I pointed my browser at that URL up there. No, I didn't. So I'm not sure why that -- 2012 EPI thing is there. Maybe it's a quirk of the Mac. I'm not actually that familiar with Macs. I'm fairly new to Macs.
It's displaying the title of the page.
Is it? Okay, thank you. And you see I have office hours tonight, which I'm apparently missing. However, you point the browser at this particular URL, and there's a process running on the server at the Department of Statistics, and that process is called rserv. It came from Simon Urbaniak down at AT&T. It's listening for these requests, and it says, hey, there's this guy down at McKinsey, and he wants to visit this page. Start running this R script. And there's an R script there, and the R script starts running. And that R script runs some grid graphics code to produce that plot. In fact, rserv is loaded up with the EPI data ready to go. So the response time is really very good. And so there's grid graphics code that's producing that plot live. It is not a static image that's just being loaded into the page. So in fact, it's ridiculously inefficient. But it's very easy to work with and modify without having to update this huge library of plots. So this plot is actually being produced on the fly when you do this. That plot, because there's some interactivity that was actually generated ahead of time, you've got some mouse over here. It's using SVG graphics. There's a little bit of interactivity there. And I think if we were to click on any of those, it would take us to a different country. Let's try that. No, not happy with that. So this was 2012, so it's not the current live page. We might get to a live page later on. But over here, we're actually doing a k-nearest neighbor analysis to identify countries that are most similar to Switzerland with respect to certain characteristics of environmental performance. And that k-means analysis is being run in this R script on the fly every time someone visits the page. Okay, and the R code to do this behind the scenes is very standard. If you use R, you could do this. A lot of you have probably done k-nearest neighbor analysis. Take your analysis to do that, stick it in the script, spit it out in a certain way. You probably need a web developer to give you CSS style sheets so it actually looks reasonable. I didn't do that part of it. And I need to go back to, where am I? Here. Back. Good. Okay. So who knows something about CGI scripting? Oh, good. Not too many people. So I'm going to give you a quick little crash course. So it stands